Okay, good morning, everyone. Sorry about that. We had a little technical glitch with our live stream website, and we're all set to get started. So welcome to yet another round of capstone presentations. We're excited to be getting this done. The students have put a ton of hard work into their research and their presentations. And I know we're short on time because of that slight delay. So I'd like to introduce Kang Lu, who will be presenting on cellulose cross-linking. Kang, it's all yours.
Okay. Good morning, everyone. And today I will be presenting about my capstone project on cellulose cross-linking. So let's start with what is all that? What is cellulose and what is cross-linking? And cellulose, you might have learned it in bio, but it's just a glucose polysaccharide. Poly stands for many, and saccharide stands for sugar. So it's a sugar polymer. And cross-linking is, so cellulose fibers are connected to each other with hydrogen bond, and the cellulose cross-linking is basically a process of treating the cellulose fibers with an organic molecule known as cross-linker, which replaces the relatively weak hydrogen bond with a stronger covalent bonding. This process reinforces the bond between cellulose fibers, which result to changing macroscopic behaviors of the material, including, but not limited to, an increased tensile strength both when dry and wet, resistance to wrinkling, and an increase in brittleness of the fabric. As of why I choose cellulose cross-linking, the very first and the most important reason is that I love chemistry. So I wanted to do a capstone project related to chemistry. So I went to discuss with my chemistry teacher, Dr. Spencer, who is also my advisor, and we came to that it's adhesives and polymers is a feasible and interesting topic to look into in high school. So that gets to me thinking, because in lower and middle school, we had to glue these handouts that teacher gave us into our notebooks, and I found that every time when I do too much of the glue, I couldn't write on it, and that get me very frustrated. And I started to wonder, like, what if we can make a glue that maintains the hydrophilicity of paper so that you can still write on it and yet still have the functionality of sticking papers together. And so that's how I came up with this project. That's the initial brainstorming part, but spoiler alert, the project is gonna drift away from this glue idea very, very fast. So a few past applications of cellulose cross-linking is mainly used to produce wrinkle-free cotton. Cotton wrinkles for the same reason most natural fiber-based fabric, which also happen to be mainly composed of digested cellulose, wrinkle when they expose to water. Wetting it heavily opens the polymer structure by allowing water to penetrate the matrix of hydrogen-bonded fibers and separate them. This leads to a bunch of related phenomena, namely decreased wet strength, since you aren't dealing with strong intermolecular reactions anymore, just steric hindrance and the natural tensile strength of the paper fibers, or cotton fibers. And the volume expansion and a conformational change that come from the impingement of water. As the water leaves, this conformational change becomes locked in and usually resulting in wrinkling, because that's a lower energy state than a completely flat sheet of fabric. And the process called cross-linking joins a new ring-shaped organic compound to the polymer chains, replacing the hydrogen bond with strong new chemical bonds. Cross-linking keeps the polymer from breaking apart when in contact with water. And so the cotton fabric come out without wrinkles. So let's go back a bit. So this picture here is two cellulose fiber. They are attracted to each other through a hydrogen bond, but they are not covalently bonded. And if we can add this red thing in the middle, this is our DMD-HEU crosslinker. It can covalently bound two independent chains of cellulose polymer together, so their bond is stronger and make them harder to wrinkle. Another application of cellulose crosslinking is to use it to protect wood, which also happens to be made of primarily cellulose fibers. The wood is crossed by DMD-HEU at temperatures above 100 degrees Celsius, and due to its two methyl groups, which can react under water separation with OH groups of the wood and with itself, bridges are formed between adjacent cellulose molecules. The product from this process is on sale under the name Belmador. It has the expected dimensional stability, especially for dimensional components such as windows and exterior doors, and durability up to the best class 1. Compared to classes 3 and 4 for the untreated jaw, there are significant improvements. Next, we are going to look into the primary focused cross-linker of this project. It's called DMD-HEU, or dimethyl or dihydroxyethylene urea. This molecule consists of a 5-member ring. Here you can see this 5-member ring with a ketone group at the top, and 2 carbons adjacent to that ketone group is replaced with nitrogen. And there are 2 carbons bounded to these nitrogen atoms, and each of them has an alcohol group on it. So the red ones are the 2 carbons. These 2 carbons are bounded to highly electronegative atoms, the nitrogen and oxygen. So because the nitrogen and oxygen are more electronegative than carbon, it means that it has stronger attraction to the electrons in the bond. So it creates a partial positive charge on the 2 carbons. The partial positive charge make the carbons more attractive to electrons, and so essentially making them a good electrophile during the reaction. We know electro stands for electrons, and phile stands for having attraction to. So that it can react with nucleophilic alcohol. And the mechanism of cross-linking process is ultimately a dehydration condensation process in which one OH group and one H plus here is removed and become an water. And I'm going to use an analogy about school bullying, in which a bully, this one, where is it? This one here, this electron pair is a bully, kicks away someone from the group, because carbon only have 4 bounding domains. So if you want to form a new bond, right, you have to kick someone away. So this nucleophilic electron pair, nucleo stand for nucleus and philic stand for attractive to. This nucleophilic electron pair attack this partial positive carbon right over here, and it kicks the OH group over here off from the carbon. It saying like the electron pair bully is saying like, we are going to have a party with that carbon, and guess who's not invited? You. Right. And that's the reason why we often use acid catalysis with cellulose cross-linking with DMDHEU, in which the acid is used to protonate the OH group on the partial positive carbon to make it an OH2+. The proton here can react with the alcohol group to make it an OH2+, which is the better leaving group, and to facilitate the nucleophilic attack. So the OH2+ will be like, I don't want to go to your stupid party anyway. Ciao. And it just go and mind its own business as a water molecule. I don't know, maybe he has a capstone project of his own. And right, and because the OH2+ is a better leaving group, it facilitates the whole reaction. So the oxygen and the carbon formed a new bond, and it linked together. And our nucleophile and electrophile lived happily ever after. We say that they are covalently bounded. There are other cross-linkers used in the industry that we didn't go in depth in this project, such as this protein cross-linker derived from Clostridium cellulovirens. It was fused to form a cellulose cross-linking protein, and the recombinant bifunctional cellulose binding protein was expressed in E. coli, applied by immersion onto Whatman cellulose filter paper, and its mechanical properties were tested. The purified protein improved the treated paper mechanical properties such as tensile strength and energy to break. In addition, cellulose cross-linking protein treatment was shown to transform filter paper into a more water-repellent paper, which is not what we intentionally to do, but yeah. The binding of cellulose binding domains to cellulose fiber under a wide range of environmental conditions without the need of chemical reaction, because proteins are cool. So you can imagine protein as a very sophisticated chemical machine that can do everything on its own. And so it can perform the cross-linking process on its own without the needing of a ton of reactions and catalysis and stuff. So it's also have a good biodegradability to make them attractive moieties for the design of new class of paper modification materials. Another cross-linker used is polycarboxylic acid. It's investigated for improving the wet performance of paper. It was reported in the literature that significant improvement in the wet strength retention and dimensional stability was achieved when the paper was treated with BTCA, or 1,2,3,4-butane tetracarboxylic acid. Among the various polycarboxylic acid investigated, BTCA has been the most effective cross-linking agent for both cotton and wood cellulose. However, the exceedingly high cost of BTCA has prevented its application on a commercial scale. And here's the experimental procedures of cellulose cross-linking. When I was looking up for the experimental procedures, I thought I'm going to do it replicate it in a school lab, so I found one without the acid catalysis. But first, you have to synthesize the cross-linker on your own, because the major chemical companies either doesn't sell to individual customers, or they sell to you at a really ridiculous price. I think it's $300 for 10 grams of this DMDHEU. So yeah, I found it. So the synthesis of DMDHEU comprised of reacting relative amounts of 1 moles of urea from between 0.8 to 1.3 moles of glyoxal and from 1.6 to 2.5 moles of formaldehyde in an aqueous medium at a pH maintained above 7 and at a temperature maintained between 30 and 100 degrees Celsius. Preferably, the mole ratios employed are relatively amount of 1 mole of urea with 1 mole of glyoxal and 2 moles of formaldehyde. Applicants have found this uniformly good result have been achieved by adhering to the mole ratio within the preferred limits. And as indicated, the aqueous reaction medium must be maintained at a pH above 7 and preferably between 7.5 and 9.5. So the alkaline pH is obtained by adding sufficient alkali to provide the initial alkaline pH and by the continuous addition of suitable alkaline materials during the course of the reaction. Suitable alkalines include sodium hydroxide, potassium hydroxide, sodium carbonate, and their equivalent. As of the cross-linking process it's on, the paper is patted twice to about 90% wet, and it pick up the using your DMDHU solution in the presence of ammonium sulfate catalyst, and the catalyst concentration was 10% of the amount of DMDHEU. The soaked paper is pressed between the squeezing rolls at 40 psi or around 2.7 atmospheric pressure and dried on a drum dryer at 80 degrees to prevent curing. And then the padded fabric will dry at 80 degrees Celsius for 5 minutes, cured and soaked and cleaned. So that rolling squeezing part was primarily the reason why I concluded that it's not very replicable in school lab, because you need this huge industrialized machine to do the squeezing process. You can press it really hard with your hand if you trust your muscle, but I don't know if it will work as well as intended. But anyway, even if we are not going to do it, it's still important to look into the safeties. And because acid and bases are used and they can cause severe burns, and so you definitely want to use your personal protective equipment indicated on the safety sheet of the specific acid and base you are using. You really don't want to get these stuff into your eyes or whatever. And also you want to work where an emergency shower is available so that you can wash it off immediately when things went south. And also because the synthesis of DMDHU includes working with formaldehyde, which is a very nasty carcinogen. So you want to make sure that you work inside a fume hood, but even that, it's still a nasty carcinogen. So it would be in your interest to not replicate this experiment at home. And finally, we are going to discuss some possible applications of cellulose cross-linking applied to papers. And it differs significantly from the initial idea of using it as a glue, because the use of acid catalysis and the requirement of padding makes the cross-linking hard to replicate in a school lab, let alone everyday life. I mean, if Mr. Cruz hands you a handout, he certainly doesn't want you to take out some acid and start cross-linking it to your notebook. But however, cellulose cross-linking still have the potential to create papers with better wet performance. And such papers could find applications in areas such as recyclable straw or food packaging. If you have used a paper straw, you might find it very difficult to use. It's gonna be good for like 3 minutes and that's it. Because regular paper straws doesn't have good wet performance. But if we can create this stronger paper material that doesn't break as easily when in contact with paper, we can make paper straws great again. And it might find application in other biodegradable food packaging areas. And yeah, that's it. I want to thank Dr. Martin and Dr. Spencer for all 1 year of continued help. For Dr. Spencer, it's 3 years of continued help. And thank you so much. Thank you. And yeah.
Very well done, Kang Peng. Thank you very much. I think it's important to note that while Kang Peng was in the class and he has thanked me, Dr. Spencer obviously helped him a ton. I didn't even help him with the humorous bits of, the presentation. That was all him or Dr. Spencer. So really well done, Kang Peng. I happen to be wearing a cotton shirt that is wrinkle-free. And it's something that has changed my life in innumerable ways over the past 10 years. So I'm glad to see that you're looking to make straws great again, although paper straws great again, although I'm not sure they were ever great to begin with, but they do have a wonderful application. Are there other applications for this, either in clothing, in paper uses, that the audience might like to hear about?
I have found an article saying that cross-linking have been used to produce those fire suits that the fire department use. Also, for the use of producing cotton-free fabric, wrinkle-free cotton, while the cross-linking technology is still being used, the specific cross-linker DMDHU is not heavily used anymore because it contains formaldehyde, and as I said, formaldehyde is a nasty carcinogen, and also the acid catalysis part will make the cotton weaker. So yeah, it's the very specific cross-linker is pretty much no longer used in the industry.
Thank you. Does anyone have a question for Kang Peng? Sophia.
Are you thinking of studying chemistry as a major in college?
Yes, I will be majoring in chemistry.
A decision about where you're going.
Yep.
Where are you going?
I committed to Carnegie Mellon.
Congratulations. Great school. Obviously, a lot of hard work that goes into earning acceptance to a school like that. But it's neat that you've been able to tap into your curiosity. I think it's also interesting to see how the research journey changes. You start with one idea, you get confronted with an obstacle. Was it frustrating to hit that obstacle early in the process and think, oh my gosh, what am I going to do? I've gone so far with this idea, and now I've got this obstacle I've got to overcome.
Very.
Yeah. So, but you adjusted very well and found a way to get around it. But it can be frustrating. Other questions for Kang Peng? Okay.
First of all, great job on your presentation. I really enjoyed it. So after hearing from you, I know I had very basic understanding of the variety of applications of cellulose cross-linking. So I have this question. Can you use cellulose as a sweetener in your drink and stuff? Like sweetener?
Sweetener?
Yes.
Thank you.
So the answer is no, because cellulose is a polysaccharide. I mean, it's made of sugar, but you can't easily make it taste like sugar. It's a sugar polymer that humans are unable to digest. There is a glucose polymer that you are able to digest though, and it's very similar to cellulose, and that is starch. So starch can taste a bit sweety, and that, but you usually don't use starch as a sweetener as well. So my answer would be no.
Oh, a thickener, maybe. It's used
Yeah.
mainly as a thickener,
Yeah.
right?
There are bacteria in those grass eating animals that can digest cellulose break it down into sugars and for it to be absorbed, but unfortunately we couldn't do it. So yeah.
Thank you. Well, Kang Peng, really well done. We're proud of you. Thank you for contributing to the field of knowledge. Well done.
Thank you so much.
If you'll just give me about 1 minute, we'll get set up for Khaleesi, who is up next. 1 second.